In this lecture, we'll discuss the third law of thermodynamics. Till now, we have studied the zeroth, first, and second laws of thermodynamics and their consequences. To end this course in this lecture, we now discuss the third law of thermodynamics. The theoretical and practical importance of this law is much less than the other laws of thermodynamics, and no wonder we are discussing the third law at the end of this course. We have seen earlier that the second law of thermodynamics introduces entropy as a state property, that is, ds is equal to dq reversible over t. And if we integrate this equation for a reversible path, then we get the change in entropy is equal to this integral. So the second law allows us to evaluate entropy up to an additive constant. So if we choose state A as the reference state, then we can determine the entropy at state B up to an additive constant. But the third law ascribes a universal value to this additive constant in the limit that t tends to 0. Therefore, if we take the limit of integration from 0 temperature, then the third law allows us to determine this additive constant S0 in the limit that the absolute temperature is 0. Now, the bulk of the thermodynamics does not require this law, because in thermodynamic analysis we are usually interested in entropy differences. However, the expressions of Helmholtz free energy, that is F is equal to U minus ds, and the Gibbs free energy, that is H minus ds, if you use the value of entropy, then they have this term S0 T plus constant. Therefore, if this S0 is not defined, then these Helmholtz free energy and the Gibbs free energy potentials are indeterminate up to a linear function of temperature of the form S0 T plus constant. Therefore, the question arises, what is this value of S0? So the answer to this question, that what is this limiting value of S0, is given by the third law. So the nature provides us with the simplest and mathematically most satisfying answer to this question, that what is this constant S0, and that is the third law of thermodynamics, which we'll directly state as that as the temperature of a system tends to absolute 0, its entropy tends to a constant value S0, which is independent of any thermodynamic variable. What we mean by thermodynamic variable over here is that if we have any variable such as pressure and let's say some other variable such as magnetic field intensity, etc., then in the limit that t tending to 0, the entropy will not depend upon these other thermodynamic variables, and in the limit of t tending to 0, the entropy of a system tends to a constant value S0. This value may not be 0, but we may assign a constant value to this S0 equal to 0, so that entropy of every substance becomes normalized in an absolute way. But this is not a strict requirement. We'll just simply assign a value of S0 equals to 0. And if we do so, we assign value of S0 equals to 0, then it also removes the indeterminateness in the potentials F and G. And this formulation was given by Max Planck. But historically, the third law evolved from the Nernst heat theorem, which was given back in 1907. And according to the Nernst heat theorem, the entropy change of a system in any reversible isothermal process tends to 0 as the temperature of the process tends to absolute zero. That is, the Nernst heat theorem says that in the limit that the absolute temperature tends to zero, if you have an isothermal process that is reversible, then the change in entropy for such a process is zero in the limit that the temperature of the process tends to absolute zero. In other words, if we denote any independent thermodynamic variable, let's say x, and x can be pressure or magnetic field intensity, then what the Nernst heat theorem says that the derivative del S by del X at constant temperature tends to zero as T tends to zero, and here X could be, let's say, the pressure. But note that this form of the third law is somewhat weaker, and we will use the statement given by Planck that is given over here. The statement of Planck is more general than the Nernst heat theorem. So now that we have stated the third law of thermodynamics, we can look at the consequences of the third law. We can discuss the consequences by considering a homogeneous system of a pure substance. And the first consequence of the statement of the third law that we have given above is that the heat capacities Cp and Cv tend to zero as temperature tends to zero. That is, the absolute temperature tends to zero. So to understand this, let's consider that entropy S is a function of temperature and some other independent thermodynamic variable. For example, X could be pressure or the specific volume. And let's just look at the entropy per unit mass. So let's just consider the specific entropy and specific properties. So what we can do is we can write ds is equal to del S by del T at constant x times dt plus del S by del x at constant t times dx, and we can also write TdS as this. This is just from the fact that S we are writing as a function of temperature and some other independent thermodynamic property such as pressure or specific volume. But note that TdS is equal to dq. Therefore, if we consider a case where x is constant, then dx is equal to 0. Therefore, we get dq by dt, that is the heat capacity at constant x, from here would simply be T del S by del T at constant x. And this is the case when x is kept constant. For example, if pressure is kept constant, then the heat capacity, that is the specific heat capacity at constant pressure Cp, would be given by T times del S by del T at constant P. Similarly, the specific heat capacity at constant volume is given by T times del S by del T at constant V. Now, from these two definitions, we can clearly see that for a process, let's say, where pressure is kept constant or specific volume is kept constant, then we can integrate, and let's write S is a function of temperature and specific volume from here, and this is S minus S naught, and we get this relation. Similarly, from this equation we can write And what we can do is, by following the convention, we can set the value of S naught to be 0 so that we normalize the values of entropy. Now, note that in the integrand, the absolute temperature is in the denominator. Therefore, at the lower limit, that is temperature equals to 0, if the heat capacities are finite, then the integral would diverge because the denominator will tend to 0 at the lower limit of absolute temperature to be 0. Therefore, we conclude that the specific heat capacities must tend to 0 as T tends to 0. Another consequence of the third law is that the coefficient of thermal expansion tends to 0 as the absolute temperature tends to 0. Recall that the coefficient of thermal expansion is defined as this, that is the derivative of the specific volume with respect to temperature at constant pressure divided by the specific volume. Now we can recall the Maxwell's relation. So if you consider the Gibbs free energy, and we have dG is minus S dt plus V dP. Therefore, from here, because dG is an exact differential, that is how we derive the Maxwell's relation. So we get del S by del P at constant T is equal to minus del V by del T at constant P. So what we have is that as the temperature tends to 0, S, that is entropy, will tend to S naught, and this limit S naught is independent of pressure. That is what the Planck's statement says. Therefore, this term, that is the derivative of entropy with respect to pressure, will tend to 0 as temperature tends to 0, and therefore, because we have del V by del T at constant P tends to 0 as temperature tends to 0, we have that the coefficient of thermal expansion would also tend to 0 as the temperature tends to 0. In fact, using the same arguments, we can also consider the limit of this derivative in the limit that T tends to 0. Now recall that from the Maxwell's relation derived from the Helmholtz free energy, this del P by del T at constant V is given by del S by del V at constant T. So using the same arguments, that in the limit that T tends to 0, then entropy tends to a constant value that is independent of pressure or volume, and therefore del S by del V will also tend to 0 as T tends to 0. Therefore, del P by del T at constant V will also tend to 0. So these are the simple consequences of the third law of thermodynamics. Another important consequence of the third law is the Nernst unattainability principle, and this principle states that any thermodynamic process cannot reach the temperature of absolute zero by a finite number of steps. To rationalize this statement, consider that we have a system that is cooled by varying some independent thermodynamic variable x from the initial state, let's say xi, to the final state xf. So let's say we plot entropy versus temperature, and we plot the lines for constant x. So here x is equal to xf and here x is equal to xi. So consider that we are initially at this state, that is x is equal to xi and temperature is this much, and we want to go to a lower temperature by changing this independent variable to xf. For example, in an expansion process, you reduce the pressure. For example, in an isentropic expansion process, these contours will be for constant pressure, and you can go from a high pressure to low pressure so that you expand the gas, let's say, and you isentropically reduce the temperature. So similarly, one can vary any independent thermodynamic variable and reduce the temperature of the system by changing that thermodynamic variable. Typically, very low temperatures are attained using the so-called magnetocaloric effect, where cooling is achieved through adiabatic demagnetization. There, X is the magnetic field intensity. But without going into details of this effect, you can consider X to be any independent thermodynamic variable. Now, consider that we have a process where the initial temperature is Ti and the system cools to a temperature Tf. So what we can do is we'll consider S as a function of T and X. Therefore, ds we can write as del S by del T at constant x dt plus del S by del X at constant T dx. We've already seen that if we write T del S by del T at constant x, it is the heat capacity at constant x. For example, if x is pressure, then T del S by del T at constant P is equal to the heat capacity at constant pressure. Now, what we can do is, while keeping x constant, we can integrate over temperature, and what we will get is, so if x is constant, so this term would be 0, so we can write, let's say, entropy at this initial temperature Ti and the value xi we can obtain by integrating this from 0 to t, and what we will get is del S by del T at x equals to xi dt, and we will also get an constant, that is S of 0 comma xi on the left hand side. So the difference in entropy at temperatures Ti and the absolute 0 while keeping x equals to xi is equal to this integral on the right hand side. Similarly, we can write the entropy at this point, that is at x equals to xf and T equals to the final temperature, and that can be written as, so we have this difference is equal to this integral. Now, from this diagram, it is clear that to get the maximum cooling effect, let's say if the system goes from this state to this state, then we won't get the maximum cooling. To get maximum cooling, we will have to go through a reversible adiabatic process where the entropy does not change. We cannot go through this process because that means we will need heat transfer to a lower temperature thermal reservoir. That means we already have that low temperature. So the idea is that we want to get cooling, and that can be done in a reversible adiabatic process, and we want to get temperatures that are lower than any other thermal reservoir. So in an adiabatic process, if we change the variable from xi to xf through a reversible adiabatic process, that is at constant entropy, we will get the maximum cooling effect. And that means if we equate this term and this term, that is entropy at this state and this state, we are equating, and what we will get is this equation. Now what we can do is that we can now invoke the third law of thermodynamics. Till now we have not invoked the third law of thermodynamics, but the third law of thermodynamics says that this value, that is entropy at absolute zero, is constant, and that constant is not dependent upon any independent thermodynamic property. Therefore these two terms should be equal, this term, and we can cancel out these terms. And note that here the limit is Ti, because we have Ti over here, and Tf because Tf is over here. So we have Ti and Tf. Now what we see is that this integral on the left hand side from 0 to temperature Ti is equal to this integral 0 to temperature Tf. Now let's just set Tf to be 0, and because the limits are from 0 to 0, this will also cancel out. So the idea is that what we want to do is we want to cool from initial temperature Ti to the final temperature, that is the absolute 0. So that's why we have set Tf to be 0. So what this gives us is 0 to Ti del S by del T is equal to 0, where Ti is the initial temperature of the system from which we are trying to attain absolute 0, and Ti is a finite temperature. And now we can see that this integrand is essentially the heat capacity at constant x over T, and the integral is over 0 to Ti, and this we are saying is equal to 0. But the heat capacity at finite temperatures is positive, and only in the limit of T tending to 0 it will tend to 0. So heat capacity cannot be negative, and therefore it is impossible for this equation to hold. So this equation to hold is impossible. Therefore, what we have shown here is that we started off by an assumption that through a finite process where we can change the independent thermodynamic variable from xi to xf in a reversible adiabatic process, we can cool the system to a lower temperature Tf, and we said that we can cool to Tf equals to 0, which gave us this equation. But this equation is impossible to hold. Therefore, what we have shown is that the absolute 0 temperature cannot be attained by a finite process. And if the absolute 0 temperature cannot be attained in a finite process, then it cannot be attained in a finite number of finite steps. Therefore, what we have is that any thermodynamic process cannot reach the temperature of absolute 0 by a finite number of steps. That is, the point of absolute 0 temperature can only be attained asymptotically. And all this follows from the fact that at absolute 0, entropy is not dependent upon any independent thermodynamic property, and it attains a constant value. And note that here in this derivation we've not assumed that S at absolute 0 is 0. All we have considered is that it attains a constant value that is independent of any other thermodynamic property. So to understand why the statement of third law leads us to this conclusion that the absolute zero temperature can only be attained asymptotically. Let's again look at this process of cooling a system by varying the independent thermodynamic property X. So what we have is, again, we have entropy versus temperature, and what the third law says is that if we plot the lines for constant X, then they should converge to the same point at t equals to 0, and this is S naught. This is the line for X equals to xf, and this is the line for X equals to xi. So imagine that the system is initially at this temperature and we cool the system, and to obtain maximum amount of cooling we need to do a reversible adiabatic process where X is changing, and in that case the system goes from this state to this particular state where the temperature is lower. Now if you want to further reduce the temperature, one way to do it is that you can go back to this state X equals to xi but at lower temperature, and then try to have this reversible adiabatic process back to X equals to xf, and you can keep on doing this. But the way these two lines of constant X are that they converge at a common value S naught at t equals to 0 means that you can keep on doing this process and go in steps, although you would go very close to t equals to 0, but you will never be able to exactly reach t equals to 0. And this is because both of these green lines corresponding to X equals to xf and X equals to xi, they both converge to a common point. Had this not been the case, for example, if the line for constant X for X equals to xf at t equals to 0 had a different limit than S naught, let's say it had this limit, let's call this as, let's say, S naught prime for xf, then what one could do is one could simply start from this point and continue up till here. But this is not allowed by the third law. What it says is that both of these curves should meet at a common point, and that leads to the Nernst unattainability principle, that in a finite number of steps you cannot attain absolute zero temperature. Therefore, the Nernst unattainability principle leads us to conclude that a Carnot cycle with heat rejection at absolute zero temperature and thermal efficiency of eta equals to 1, that is 100% thermal efficiency, is impossible, because recall that the thermal efficiency of a Carnot cycle is 1 minus the temperature at which heat is rejected divided by the temperature at which heat is absorbed. So if we were able to attain the absolute zero temperature, efficiency would tend to 100%, but the Nernst unattainability principle says that you cannot reach this absolute zero temperature in finite number of steps, and absolute zero can be attained only asymptotically. Therefore, we cannot have a Carnot cycle which rejects heat at zero temperature, and therefore a Carnot cycle cannot have thermal efficiency of 100%. So this concludes our discussion of the third law. To end this introductory course on thermodynamics, let us just look at an interesting way to think about the laws of thermodynamics now that we have discussed all the laws of thermodynamics and their consequences. So this is an informal way of presenting these laws in a very interesting way. So consider that you are playing a game of converting heat to work, and the nature imposes certain rules for this game. And these rules that the nature imposes are the laws of thermodynamics. And these laws describe what you cannot do if you wish to convert heat to work. And the rules are: the first rule, that is the zeroth law, is that you cannot ignore the temperature of your heat engine if you wish to convert heat to work. Then the first law says you cannot extract more work than your heat intake. The best you can do is to break even. That is the maximum amount of work that a heat engine can deliver, that is equal to the heat intake of the heat engine, and that is what the first law says. But then comes the second law, that is another rule that the nature imposes if you wish to convert heat to work. And the second law says that you cannot even do that much amount of work that is equal to the heat intake, and you cannot break even unless you reach the absolute zero temperature. But the third law comes and it says that you cannot reach absolute zero temperature in your lifetime. So what do you think about your prospect in this game?